The number comes first, 12 seconds of arc. That is the measured deviation of the base corners of the Great Pyramid from a perfect right angle, not 12 degrees, not 12 minutes, 12 seconds, 1/300th of a minute, 1/24,000th of a circle, across a base more than 230 meters long. That figure is not poetic, it is not symbolic, it is not a metaphor, it is a measurement, and it immediately creates a problem. A right angle is 90 degrees. In modern engineering, holding that angle precisely across large distances is not trivial. 12 arc seconds of deviation corresponds to an error of roughly 7 millimeters across the length of a football field, on a structure made of over 2 million stone blocks, each weighing tons, set without mortar, laid 4,500 years ago. This is the measurable engineering fact that does not match the assumed technological capability. To understand why, the scale of the number must be understood. An arc second is an angular unit so small that it is rarely used outside astronomy, geodesy, and high-precision surveying. When modern surveyors measure angles to that resolution, they do not rely on ropes or human eyesight. They use optical theodolites with finely machined glass circles, digital total stations with electronic angle encoders, or laser-based instruments referenced to factory-calibrated standards. These tools exist because without them, errors multiply invisibly. Now consider the environment of Old Kingdom Egypt. No metal reference squares, no precision ground surfaces, no optical lenses, no calibrated angular scales. No surviving instruments capable of resolving even 1 minute of arc, let alone seconds. The documented tools consist of ropes, plumb lines, wooden sighting devices, water levels, and astronomical observation by naked eye. And yet the stone records the result. The four corners of the pyramid meet at angles closer to 90 degrees than many modern concrete foundations poured today. Modern masonry tolerances for large structures often allow deviations of several millimeters over short spans and significantly more over long distances. High precision work is possible, but it is slow, expensive, and dependent on feedback instruments. Even with modern tools, achieving that level of squareness across 200 meters requires constant verification. Verification is the key word. Precision is not just about making something straight or square once. It is about knowing that it is straight or square, and being able to check it repeatedly as work progresses. In modern engineering, this is handled through closed measurement loops. One instrument checks another. Reference points are tied back to standards. Errors are detected before they accumulate. Remove those instruments, and the problem becomes fundamentally different. Imagine attempting to lay out a square the size of several city blocks using nothing but rope and stakes. A rope can define distance, but it stretches, it sags, it responds to humidity and tension. A plumb line can define vertical but not horizontal angle. A water level can establish flatness but not squareness. Astronomical observation can establish cardinal direction, but converting that direction into four precise 90-degree corners requires transferring angular information across space without distortion. Each step introduces uncertainty. Each correction depends on the previous step being accurate. And yet, the final geometry does not show the fingerprints of accumulated error. It shows control. 12 arc seconds is not the kind of number that appears by chance. Random error does not cluster so tightly. Human estimation does not accidentally converge on arc-second precision across hundreds of meters. If this were a small shrine or a single stone, coincidence might be plausible. But this is a perimeter more than 900 meters long. To make the scale concrete, consider modern road construction. Survey crews laying out highway alignments typically work with tolerances on the order of minutes of arc, not seconds. For most purposes, that is more than sufficient. Buildings stand, bridges hold, deviations are invisible to the eye. Achieving tighter tolerances is possible, but it is not standard practice because it requires more time, more equipment, and more verification. The Great Pyramid exceeds those ordinary requirements by an order of magnitude. This is not a claim that ancient builders possessed secret technology. It is a statement that the outcome demands explanation beyond casual hand-waving. Saying they were very skilled does not address the mechanics of how that skill was applied, measured, and confirmed at scale. Consider also that the base of the pyramid is not only square, but level. The variation in height across the entire foundation is on the order of 2 centimeters. That flatness was achieved on bedrock, without concrete, without steel forms, without laser levels. Again, modern builders can do this, but only with instruments specifically designed to detect deviations smaller than the thickness of a finger. Skill alone does not create numbers like this. Systems do. This leads to the central question, stated plainly and without embellishment. How did a society working with stone, wood, rope, and human vision achieve and verify angular precision that, in modern contexts, is normally associated with industrial-grade surveying instruments? This question does not require speculation about lost civilizations or advanced outsiders. It requires a sober assessment of process. What methods could produce such results? What error-checking loops were available? How was accuracy maintained over time, especially as construction progressed and reference points were buried, removed, or altered? Some propose simple geometric methods, such as stretching ropes in 3-4-5 ratios to create right angles. On a small scale, this works. On a large scale, rope elasticity becomes a dominant source of error. Others suggest astronomical alignment using circumpolar stars to establish true north, then rotating 90 degrees from that line. But rotating an angle is itself an angular measurement problem. Without a protractor or calibrated arc, rotation relies on indirect constructions that amplify small mistakes. What is striking is not that such methods exist in theory, but that the resulting structure shows no clear trace of their limitations. The pyramid does not wobble slightly off square. It does not drift noticeably at one corner. Its errors are small, consistent, and symmetric. That pattern implies deliberate control rather than approximation. This is why the measurement matters. It anchors the discussion. It prevents the conversation from drifting into abstraction. The stones either form angles this precise or they do not. Survey data says they do. So the puzzle is not whether ancient Egyptians were capable of remarkable feats. That is beyond dispute. The puzzle is whether our simplified picture of their tools and methods is sufficient to explain the exactness we can measure today. If it is sufficient, then those methods should be demonstrable, repeatable, and capable of producing the same results under controlled conditions. If it is not, then something is missing. Not something mystical, but something practical. A technique, a workflow, a system of verification that left little trace except in stone. And that is where this journey begins. Not with wonder, but with a number that refuses to be ignored. Before the question can be answered, the terms must be disciplined. Precision is not the same thing as beauty. It is not the same thing as craftsmanship. And it is certainly not the same thing as ambition. Craftsmanship is the ability to shape material with care and consistency. A skilled mason can cut stone cleanly, align blocks neatly, and create surfaces that appear straight and true to the eye. Precision, in engineering terms, is something colder. It is numerical. It is the controlled minimization of deviation from an abstract ideal, measured against a defined reference. Precision is not what looks right. It is what measures right. This distinction matters because many historical explanations blur the two. They praise ancient builders for their artistry and dedication, then quietly assume that precision simply emerges from enough effort. It does not. Precision emerges from constraint, measurement, and verification. Without those, effort produces variation, not convergence. To understand why the measured angles matter, angular measurement itself must be unpacked. A full circle contains 360 degrees. Each degree is divided into 60 minutes, each minute into 60 seconds. An arc second, then, is 1 part in 1,296,000 of a full rotation. It is not an intuitive unit. It exists because there are situations where larger units are too coarse to describe reality accurately. Surveyors use arcseconds because small angular errors translate into large positional errors over distance. A deviation of 1 degree is obvious immediately. A deviation of 1 minute may be invisible at short range but becomes noticeable across a long baseline. A deviation of a few seconds can remain hidden until distance magnifies it into meters. This is why arcseconds matter. They are not about perfection for its own sake. They are about control. In modern surveying, angular precision is classified according to application. Rough layout work may tolerate errors of several minutes. General construction control might require sub-minute accuracy. High-precision geodetic work, the kind used for national mapping networks or long-span bridges, operates routinely at the arcsecond level or better. Achieving that requires specialized instruments, stable reference points, and repeated observations averaged over time. Now consider masonry. Typical modern masonry tolerances allow deviations of several millimeters over a few meters and more over longer spans. Walls are permitted to lean slightly. Corners are allowed to be a little off. These tolerances exist because structures do not need perfect geometry to function safely. Gravity is forgiving. Materials accommodate small errors. What modern practice does not do, except when absolutely necessary, is enforce arc-second-level angular control across hundreds of meters. When it does, it is treated as an exceptional task. It is planned carefully. Instruments are calibrated. Survey control networks are established. Redundancy is built in so that errors can be detected before construction locks them in place. This brings us to the rule that governs all of this. Large scale plus high precision is exponentially harder than either alone. At small scales, high precision can be achieved with simple means. A machinist can square a small metal block using hand tools and patience. At large scales, even modest precision becomes difficult. Errors that are negligible at 1 meter become significant at 100. At 200 meters, they dominate. The difficulty is not linear, it compounds. Each measurement relies on the previous one being correct. Each transfer of reference introduces uncertainty. Each physical medium, rope, wood, stone, introduces variability. Temperature changes length. Tension alters geometry. Human perception introduces bias. Without an independent way to check results, errors accumulate silently. This is why modern engineers rely so heavily on instruments. Not because they lack skill, but because skill alone cannot see what must be corrected. A laser level does not get tired. An optical theodolite does not assume. A calibrated scale does not drift without warning. When an engineer today lays out a large square, they do not simply measure one side and assume the rest will follow. They check diagonals, they close loops, they return to starting points to see whether the geometry still agrees. If it does not, they know something went wrong. This concept, closure, is central to precision engineering. A system that cannot close on itself cannot guarantee accuracy. Closure requires reference standards and measurement tools capable of detecting discrepancies smaller than the tolerances being enforced. Now remove those tools. In the context of early dynastic construction, the documented toolkit lacks any surviving instrument capable of directly measuring angles in minutes or seconds. There are no angle scales, no optical aids, no fixed reference surfaces known to be machined flat or square. The methods that are proposed, ropes, sighting, geometry, are all indirect. They can establish relationships, but they struggle to quantify deviation. Indirect methods are not useless. They can be powerful, but they are also fragile. Their accuracy depends on ideal conditions and repeated correction. Without a way to measure the correction itself, the system relies on assumption. This is where the difficulty sharpens. The pyramid's base does not merely suggest that right angles were intended. It shows that right angles were achieved with consistency that implies measurement, not approximation. The deviation is not random. It is small, controlled, and uniform. Uniform error suggests a known process operating near its limit. Random error suggests guesswork. What we see is the former. So, when modern engineers look at the numbers, they do not say impossible. They say something more precise and more troubling. That is not what we would expect from those tools. That distinction matters. Impossible is a word for myths. Unexpected is a word for engineering. The challenge then is not to deny the measurement, nor to inflate it into mystery, but to understand what level of precision should reasonably be expected from the known methods. And when the observed precision exceeds that expectation, the responsible response is not dismissal, but investigation. This is the threshold being crossed. Once precision is defined properly, once scale is accounted for, and once modern benchmarks are applied honestly, the question becomes unavoidable. If achieving and verifying arc-second level angular control at this scale is difficult even now, how was it done then? Not as a miracle, not as an accident, but as a process. And if that process is not fully described by the tools we think we know, then the gap is not in the stone, it is in our understanding.
Because precision does not happen by chance. It leaves fingerprints, and the deeper one looks, the clearer it becomes that the fingerprints are there, waiting to be explained.
When the pyramid is discussed, language often drifts toward symbolism, cardinal directions, sacred geometry, cosmic meaning. All of that sits downstream from a simpler, harder foundation, numbers taken on stone. The first serious attempt to capture those numbers belongs to Flinders Petrie in the late 19th century. Petrie was not searching for mystery. He was a surveyor by training, trained in metrology, obsessed with measurement error. He arrived at Giza with chains, plumb lines, leveling instruments, and a temperament that distrusted romance. What he recorded still frames the discussion today. Petrie measured the lengths of the four sides of the Great Pyramid's base and found them astonishingly uniform. Each side is approximately 230.3 meters long. The variation between the longest and shortest sides is on the order of a few centimeters. That alone is notable, but it is not the most important figure. More striking are the angles. Using repeated measurements, Petrie calculated that the corner angles deviated from a perfect 90 degrees by only a few seconds of arc. Later analyses refined the number, converging on deviations of roughly 12 arc seconds. This was not a single lucky reading. It emerged from averaging multiple measurements taken around the perimeter, compensating for local damage and missing casing stones. What matters here is not Petrie's authority, but his methodology. He treated the pyramid as an engineering object. He measured, cross-checked, and published uncertainties. His conclusion was cautious and restrained. The precision exceeded what he expected. In the century since, those measurements have been revisited. Modern surveys using electronic distance measurement, GPS-referenced control points, and laser scanning have confirmed the essential findings. The exact numbers shift slightly depending on which edges are reconstructed and which assumptions are made about erosion, but the order of magnitude does not change. The pyramid base is square to within a few parts in 10,000. Its corners are very close to right angles, its sides are nearly equal, and its foundation is level to within approximately plus or minus 2 centimeters across more than 200 meters. That last figure deserves attention. Leveling is often discussed casually, as if flatness were obvious. It is not. Establishing a horizontal plane over uneven bedrock is a complex task. Modern builders use laser levels, rotating reference beams that project a constant plane of light. Ancient builders did not have that option. Yet the pyramid's base does not slope appreciably. There is no systematic tilt. No corner is markedly higher than the others. The variation that exists is subtle and evenly distributed. This is not symbolic alignment. It is physical geometry. Stone does not care about intention. It records outcome. When these figures are placed together, they form a coherent picture. A square that is nearly perfect, a plane that is nearly flat, edges that are nearly equal. Each of these could be explained individually with effort and skill. Together, they point to a coordinated process. Now consider error propagation. In any measurement system, errors accumulate. If you measure a distance with a rope, the rope stretches slightly. If you sight a line by eye, your alignment drifts by a small amount. If you repeat these steps without correction, the error grows with each iteration. This is not speculation. It is fundamental to measurement theory. In small constructions, the growth of error is limited. In large constructions, it becomes dominant. A 1 millimeter error per meter becomes a 20 centimeter error over 200 meters. An angular deviation too small to notice at short range becomes obvious at long range. The pyramid does not show those signatures. Its geometry does not drift. The errors do not amplify outward from a point. They remain constrained. This implies either extraordinary luck or continuous correction. Luck can be dismissed statistically. The probability of 4 corners independently converging on near right angles within seconds of arc across such distances without feedback is vanishingly small. Continuous correction, then, becomes the only serious explanation. But correction requires detection. To correct an error, one must first know it exists. This brings the discussion back to instruments and methods. How were deviations detected? How were they quantified? How was the geometry checked as the foundation was laid out? One common explanation invokes diagonal measurement. In a square, the diagonals are equal. If they match, the shape is square. This is true in theory. In practice, measuring diagonals of over 300 meters with sufficient accuracy to detect arc-second level angular error is a challenge. Any error in distance measurement translates directly into angular uncertainty. Another explanation invokes repeated alignment to cardinal directions. Establish north, then establish east and west. But establishing east from north is itself an angular operation. It requires either rotation or geometric construction, both of which introduce error unless carefully controlled. What is striking is that the pyramid's errors are not chaotic. They are systematic and small. The sides bow slightly inward, a subtle concavity that may reflect intentional design or construction sequence. The corners are consistent in their deviation. This suggests a known method with known limitations, not improvisation. In engineering, this pattern is familiar. It is what happens when a process is pushed close to its resolution limit. The output reflects the precision of the method, not randomness. This is why the pyramid base cannot be dismissed as a symbolic gesture or an aesthetic preference. Symbolism does not produce 12 arc seconds. Ritual does not flatten bedrock to within centimeters, over hundreds of meters. Only process does. The numbers force a change in perspective. They move the discussion away from admiration and toward mechanics, away from what was intended and toward what was achieved. And once that shift occurs, a new problem emerges, because achieving precision is one challenge, knowing that it has been achieved is another. The stones tell us the result. They do not tell us how the builders confirmed day after day that the geometry remained true. Precision in isolation is impressive. Precision with verification is transformative. The pyramid base stands at that boundary. It demonstrates control, but it also implies oversight. Measurement without measurement tools is not impossible, but it is fragile. The pyramid does not look fragile. It looks deliberate, which leads inevitably to the next question, more unsettling than the first. Precision explains the outcome. But what explains the confidence to proceed, knowing that the outcome was correct? Because without verification, even the most careful builder is guessing. And guessing is not how structures like this survive. There is a question that sits quietly beneath all discussions of ancient precision, rarely spoken aloud because it is uncomfortable in its simplicity. How do you know you are right-angled if you have no reference standard for a right angle? Not how do you intend to be right-angled? Not how do you hope? How do you know? In modern engineering, this question barely registers because the answer is embedded everywhere. A machinist squares a block against a reference plate that was itself ground flat against another reference plate, traced back through a chain of calibration to a national standard. A surveyor checks an angle with a theodolite whose optics were aligned and tested against certified angular scales. Even a simple carpenter's square is only trustworthy because it was manufactured using tools more precise than itself. This is what precision actually rests on. Feedback. Feedback is the silent partner of accuracy. It is the mechanism by which error is detected before it becomes permanent. Without feedback, a system does not converge toward precision. It drifts. In precision engineering, nothing is accepted on first pass. Measurements are taken, then checked independently. Lines are drawn, then remeasured from a different baseline. Loops are closed deliberately, so that the endpoint can be compared to the beginning. If they do not match, something is wrong, even if the discrepancy is invisible to the eye. This is not a luxury, it is a necessity. Because error behaves in a particular way. It hides early. It accumulates quietly. And it reveals itself only when it is too late to correct. Now imagine removing the instruments that make feedback possible. No calibrated angle, no rigid square, no optical magnification, no numerical readout, only physical actions and visual judgment. Under those conditions, achieving a right angle once is possible. Maintaining that right angle across distance is something else entirely. A simple geometric construction can create a right angle locally. Stretch a rope into a triangle with sides in a 3-4-5 ratio, and the angle opposite the longest side will be 90 degrees. This method has been known for millennia and does not require advanced theory, but it produces a right angle only at the scale of the rope. It does not guarantee that the direction defined by that angle remains accurate as it is extended outward. To extend a line, you must transfer it. To transfer it, you must reference it to something. Each transfer introduces error. Without a way to measure that error, you cannot know how much has been introduced. This is the crux of the verification problem. The base of the Great Pyramid is not defined by one right angle. It is defined by 4. Each one must agree with the others. Each side must be straight. Each corner must close. If one angle is slightly off, the error propagates around the perimeter. By the time the final corner is reached, the discrepancy becomes unavoidable, unless it has been detected and corrected earlier. Modern surveyors deal with this by redundancy. They measure from multiple points. They triangulate. They compare results. They do not trust any single measurement, no matter how confident it appears. Confidence is not data. What would the equivalent process look like without instruments? If a builder lays out one side and establishes a perpendicular, that establishes only a local condition. To lay out the opposite side, they must either measure distance and repeat the process, or somehow project the original angle across space. Either way, the operation depends on the stability of the reference and the accuracy of the transfer. Now, consider scale again. 230 meters is not a symbolic number. It is a distance over which the curvature of the Earth itself becomes measurable if precision is high enough. It is a distance over which temperature gradients affect materials. It is a distance over which human sight loses acuity. Maintaining angular consistency across that span requires not just skill, but continuous validation. This is where the difference between achieving precision and sustaining it becomes critical. A right angle produced once can be admired. A right angle preserved across 4 sides, across time, across construction phases, demands oversight. Oversight implies monitoring. Monitoring implies tools. It is tempting to imagine that ancient builders simply laid out the base carefully at the beginning and then trusted it. But trust is not an engineering strategy. Construction disturbs reference points. Stakes are moved, ropes are loosened, ground is cut and filled. If there were no way to re-establish the geometry reliably, the initial precision would erode. Yet the finished result shows no sign of erosion in accuracy. The errors are not cumulative. They are bounded. This boundedness is what forces the issue. It suggests that the builders were not merely hoping their layout was correct, they were checking it. But checking against what? Without a reference standard, there is no absolute. Without an absolute, there is no verification, only comparison. Comparisons can detect inconsistency, but they cannot guarantee correctness unless the comparison network is closed and redundant. One could imagine repeated diagonal checks, repeated distance comparisons, repeated alignments to astronomical events. All of these are possible in principle, but each one has limits. Diagonal measurements depend on distance accuracy. Astronomical observations depend on timing, atmospheric clarity, and angular resolution of the eye. None of these naturally operate at the arc-second level, and yet the geometry suggests that something approaching that level of control was achieved. This does not mean that ancient builders measured in arc-seconds. It means that the end result corresponds to what we would describe that way today. The question is how. Verification is the hidden obstacle because it cannot be faked. You can cut stone finely by eye. You cannot detect a 7 millimeter deviation across 200 meters by eye alone. Something must mediate between intention and outcome. Modern engineers recognize this immediately. When shown the measurements, they do not marvel first at the skill. They ask how it was checked. Because that question reveals whether a process is robust or accidental. So the mystery is not whether ancient builders were clever. It is whether they had a way to close the loop, to know with confidence that what they had laid out was what they intended. The stones suggest that they did. And if they did, then somewhere between rope and bedrock, there must have been a method of feedback powerful enough to restrain error across scale. Not magic, not myth. A technique, a procedure, a system. The problem is that we do not see it clearly anymore, which leaves one final pressure point. If verification was essential, and if the outcome demands it, then the absence of obvious verification tools is not a trivial gap. It is the central obstacle, because precision without verification is luck, and what stands on the Giza plateau does not look like luck at all. To move forward honestly, the inventory must be stripped down to what is actually known, not what is imagined, not what is inferred, because the outcome is impressive. Only the tools that are documented archaeologically or described in contemporaneous records. They are few. Ropes, often knotted at regular intervals, plumb bobs, simple weights suspended on cords, sighting instruments such as the Merket, essentially a straight edge used in conjunction with stellar observation, and water used as a leveling reference. These tools are not primitive in the sense of being ineffective. They are ingenious in their simplicity, but they are also bound by physical limits that do not disappear with skill. Take the rope first. A rope is a distance tool. It can define length, create straight lines under tension, and encode ratios when marked or knotted. But a rope is also elastic. Even when made from plant fiber and pulled taut, it stretches under load. The amount of stretch depends on tension, humidity, fiber quality, and age. Two pulls with slightly different force produce two slightly different lengths. In small constructions, this variability is negligible. In large layouts, it becomes decisive. A rope stretched across 200 meters will not behave the same way it does across 20. A 1% elongation over that distance is catastrophic. Even 0.1% introduces centimeters of error. Maintaining consistent tension across repeated measurements is extremely difficult without mechanical aids. There is also sag. A rope under its own weight does not form a straight line unless supported continuously or tensioned far beyond practical limits. The longer the span, the greater the sag. The sag introduces a vertical component that subtly alters horizontal distance. Surveyors today avoid this by supporting tapes, applying correction factors, or using instruments that bypass the problem entirely. Now consider the plumb bob. It is an excellent tool for establishing verticality. Gravity is reliable. A plumb line points down with remarkable consistency. But vertical is only one axis. A plumb bob cannot define horizontal angle. It cannot establish squareness. It cannot tell you whether two directions differ by 90 degrees or 89.5. It is a reference, not a measuring device. The Merket is more sophisticated in concept. It allows alignment to stars, particularly circumpolar stars that appear to rotate around a fixed point in the sky. By observing their transit, one can establish a north-south line. This is a powerful technique. It can produce true north, with impressive accuracy if performed carefully and repeatedly. But here the limits reassert themselves. The angular resolution of the human eye under ideal conditions is roughly 1 arc-minute. Skilled observers can do slightly better, but arc-seconds are beyond unaided vision. Atmospheric distortion further degrades accuracy. Stars shimmer, horizons blur, timing errors creep in. Even if true north is established within a few minutes of arc, rotating that direction into east-west introduces additional uncertainty. Each geometric construction compounds error. Without a way to measure the angle directly, the builder is relying on proportional constructions whose accuracy depends on the stability of the reference and the precision of execution. Water leveling is perhaps the most robust of the ancient methods. Water finds its own level. A channel filled with water defines a horizontal plane. This can be extended across distance by digging trenches or using linked vessels. In principle, this allows the establishment of flatness over large areas. But water leveling defines only elevation, not plan geometry. It tells you whether points are at the same height, not whether they are arranged in a square. It solves one dimension of the problem, not the others. When these tools are combined, they form a toolkit capable of impressive feats. They can establish straight lines, verticals, horizontals, and cardinal directions. What they struggle to do is quantify deviation at very fine scales, especially over large distances. This is where expected error ranges become relevant. Consider rope-based distance measurement. Even with careful tension control, errors of several millimeters per 10 meters are plausible. Over 200 meters, this accumulates into centimeters. For angular construction, a small distance error translates into an angular error that grows with baseline length. Human sighting error, even under optimal conditions, is measured in arc-minutes. Repeated observations can reduce random error through averaging, but systematic biases remain. Without optical aids, the lower bound is stubborn. Environmental distortion adds another layer. Heat shimmer near the ground bends light. Wind moves ropes. Temperature changes alter material length. None of these effects are dramatic in isolation. Together, they form a background noise that precision systems must overcome. Modern instruments exist largely to suppress this noise. They isolate measurements from environmental variables or compensate for them mathematically. Ancient tools could not do this explicitly, so if one were to model expected outcomes from these tools, assuming careful use and repeated correction, one might reasonably expect right angles accurate to within a degree or perhaps a few minutes of arc over moderate distances. That would already be impressive. It would be more than sufficient for functional architecture. But the pyramid base does not sit at that level. It is an order of magnitude tighter. This is the point where explanations often retreat into vagueness. Phrases like remarkable skill or lost techniques appear. But skill does not alter the elastic modulus of rope. Technique does not sharpen the human retina. Experience does not eliminate atmospheric refraction. The tools impose ceilings, and yet the stone appears to exceed them. This does not mean the tools were insufficient in absolute terms. It means that, as currently understood, their expected error ranges do not align cleanly with the measured results. Either the tools were used in ways not fully appreciated, or additional procedures existed that amplified their effectiveness, or the measurement interpretation itself is flawed. Those are the only options that remain grounded in reality. What can be said with confidence is this. If one were to hand these tools to a modern engineer and ask them to lay out a square of 230 meters with arc-second level accuracy, they would hesitate. not because it is impossible, but because without instrumentation the process would be fragile, slow, and uncertain. The Great Pyramid's base does not look fragile, it looks controlled. That tension is the heart of the problem. The math suggests the tools should struggle. The environment conspires against precision. Error should creep in. But it does not, at least not to the degree expected. The stones say one thing, the tool limits say another. And between them lies a gap that cannot be closed by admiration alone. Error does not announce itself. It accumulates quietly, invisibly, and with remarkable patience. This is the property that makes scale such a ruthless adversary to precision. At small distances, in small constructions, inaccuracies can hide indefinitely. At large distances, they cannot. They surface, magnified by geometry itself. Imagine laying out a right angle across a floor 3 meters wide. A slight misalignment, 1 or 2 millimeters at the corner, goes unnoticed. The walls still meet. The room feels square. The deviation is swallowed by the limits of perception and material tolerance. Even if the angle is off by a fraction of a degree, the consequence is negligible. Human construction evolved for millennia within this forgiving regime. Now stretch that same angle outward. Keep the same fractional error. Extend the lines not 3 meters, but 230. The misalignment no longer hides. The two lines diverge visibly. The corner refuses to close. A gap opens where stone should meet stone. Geometry becomes unforgiving. This is not a matter of opinion. It is mathematics. Angular error grows linearly with distance. A deviation of a single arc minute produces an offset of roughly 6 to 7 centimeters over 200 meters. 12 arc seconds, the number etched into the pyramid's base, corresponds to millimeters. That is the difference between a corner that nearly closes and one that fails outright. This is why scale changes everything. In engineering, this phenomenon is called error stacking. Each measurement, each alignment, each transfer of reference introduces a small uncertainty. On its own, that uncertainty is harmless, but measurements are not isolated. They are chained together. One establishes the next. Over time and distance, the uncertainties accumulate. If a surveyor measures a baseline with a slight error, then erects a perpendicular from that baseline, the angular error is inherited. If that perpendicular is then extended, the inherited error grows. If another perpendicular is erected from that line, the original error is now embedded twice. Without correction, the system drifts. This is why modern surveyors do not trust sequential construction. They build networks. They create closed loops where the final measurement returns to the starting point. If the loop does not close, the error is revealed. The discrepancy can be distributed, minimized, or corrected before construction proceeds. These techniques are not optional at large scale, they are survival mechanisms. Consider how a modern survey team would lay out a square the size of the pyramid's base. They would establish a control network first, using multiple reference points tied together by redundant measurements. Angles would be measured repeatedly with theodolites capable of resolving seconds of arc. Distances would be measured with electronic devices accurate to millimeters. Every point would be checked from more than one direction. Closure would be enforced mathematically. Even then, the process would not be casual. It would be deliberate and slow because the consequences of uncorrected error are expensive. Now remove that framework. Without instruments capable of resolving fine angular differences, the only way to manage error is through geometry and repetition. One can compare distances, one can check diagonals, one can realign to the sky. These methods can detect gross mistakes. What they struggle to do is detect small ones before they propagate. This is where the contrast between 3 meters and 230 meters becomes decisive. At 3 meters, a rope stretched by hand defines a straight line well enough. At 200 meters, the same rope sags, stretches, and responds to every change in force. At 3 meters, the eye can judge alignment against nearby features. At 200 meters, parallax and atmospheric shimmer distort perception. At 3 meters, a small angular error produces a millimeter offset. At 200 meters, it produces centimeters. Ancient builders were not ignorant of these effects. They lived in the physical world. They knew that long distances were harder to control. This is why the scale of the pyramid base is not just impressive, but revealing. It represents a conscious decision to operate in a regime where error control is difficult. The question then is not whether they understood scale, but how they managed it. Modern surveyors manage scale by breaking it down. They establish intermediate points. They reference each point back to the network. They do not allow errors to run unchecked. Crucially, they have tools that tell them when an error has occurred. Ancient builders lacked those tools, at least as far as surviving evidence shows. They did not have angular readouts. They did not have rigid reference frames immune to deformation. They did not have a way to express error numerically and decide whether it was acceptable. And yet, the geometry suggests that error was constrained anyway. This is the tension that keeps returning. The outcome behaves as if a feedback mechanism were in place. Errors do not grow without bound. They are suppressed. The final form is stable. One could argue that the builders simply repeated the process many times, adjusting by eye until things appeared correct. But appearance is not enough at this scale. Human perception is not sensitive to millimeter offsets across hundreds of meters. The difference between a 90-degree angle and an angle off by 12 arc seconds is invisible without measurement. Another possibility is that the builders relied heavily on diagonal checks. In a square, the diagonals are equal. If both diagonals match, the figure is square. This is true, but only if the distance measurements themselves are accurate. Measuring diagonals of over 300 meters with sufficient precision to detect millimeter-level differences is a formidable task without modern tapes or electronic devices. Any slack, sag, or tension variation masks the signal. Moreover, diagonal equality alone does not guarantee that all angles are right. A rhombus can have equal diagonals under certain conditions. Multiple checks are required to rule out such configurations. The deeper one looks, the clearer it becomes that scale forces rigor. There is no shortcut. Large, precise geometry demands either instrumentation or an equivalent process that plays the same role. This brings us to a subtle but critical point. The absence of modern instruments does not imply the absence of sophisticated method. It implies the absence of modern forms of feedback. But feedback itself can take many forms. It does not have to look like a theodolite to function like one. What matters is not the appearance of the tool, but the behavior of the system. A system that suppresses error must have some way of sensing it. A system that maintains alignment across distance must have a way of comparing distant points meaningfully. A system that produces consistent results must be repeatable and robust against disturbance. The pyramid base exhibits those properties. It is robust, it is consistent, it is repeatable in its geometry. This is why the conversation cannot stop at "they were skilled." Skill explains execution. It does not explain control at scale. The modern mind often assumes that measurement is synonymous with instruments, but measurement in a deeper sense is about relationships. It is about comparing one thing to another in a way that reveals difference. Instruments are one way to do this. They are not the only way. The uncomfortable implication is that ancient builders may have been measuring, but not in the way we instinctively imagine. They may have employed procedures that encoded precision into process rather than into devices. Methods that allowed errors to reveal themselves through geometric inconsistency rather than numerical readout. If that is the case, then our inventory of tools is incomplete, not because objects are missing, but because concepts are. This is the edge of the problem now. The math is clear. Scale amplifies error. Error must be managed. The results indicate that it was, which leaves a final unsettling possibility. That the builders were not failing to measure with inadequate tools, but succeeding with a measurement logic we have not fully reconstructed. unless they were not measuring the way we assume at all. Subscribe to our channel if you love our content. Half a world away, in the high Andes, the Inca built walls that continue to defy simple explanation. At first glance, these structures are different from the pyramids of Egypt. They do not reach skyward. They do not command sight lines across the desert. They hug the contours of mountains, tracing terraces and fortresses with organic fluidity. Yet they too exhibit precision that challenges assumptions about technological capability. Polygonal masonry is the hallmark of Inca construction. Stones of irregular shape, some massive, some small, are fitted together with astonishing care. The faces of each block are not flat in the abstract sense of modern masonry, but they interlock with neighbors so tightly that not even a thin knife can pass between them. Each contact surface has a precise angular relationship to those around it. The result is a wall that resists seismic activity without mortar because the stones settle into one another mechanically. Measurement reveals the scale of the achievement. Many stones meet their neighbors with gaps measured in fractions of a millimeter. Edges that appear random at first are often aligned along planes that run for multiple meters, preserving angles that seem intentional rather than accidental. The geometry is local rather than global, but its precision is no less remarkable for that. While the pyramid demands right angles over hundreds of meters, Inca walls demand exacting fit over surfaces that curve, slope, and rise irregularly. The challenge is different, but the underlying engineering problem is the same: maintaining control of geometry at a scale and complexity that exceeds the natural resolution of human sight and touch. Attempts to explain the method rely on evidence we can observe today. Archaeologists have documented extensive use of hammerstones and chisels, with successive adjustments to shape each block until it fits perfectly with its neighbors. This iterative process is time-consuming and labor-intensive, but it offers a plausible route to accuracy. Even so, the error margins implied by the surviving walls are far smaller than what casual inspection would suggest. A single misplaced surface can propagate instability in the interlocking structure, yet the surviving walls show few such errors, implying consistent monitoring and correction. The analogy to the Egyptian case is striking. In both cases, angular control appears at a level beyond what we expect from the known tools. For the pyramid, it is arc-seconds of deviation over hundreds of meters. For Inca walls, it is sub-millimeter fit between irregular hand-shaped stones. Both feats reflect a deep understanding of geometry and a practical method for controlling error without reliance on precision instruments as we define them today. The Inca also appear to have controlled angular relationships dynamically. Many of the walls bend, rotate, or step to follow the natural contours of the mountain. Each transition requires careful adjustment of adjacent stones. A simple linear measurement cannot capture the challenge. Here, precision is not uniform, but adaptive. It is geometric intelligence applied in real time. The engineering fact is the same. The stones conform to an ideal, and the error is far smaller than expected given the tools documented in the archaeological record. Researchers who have attempted to replicate this construction using historically plausible tools consistently encounter limitations. Even with modern chisels and templates, achieving the same degree of fit requires hours of trial and correction for each stone. Human perception alone is insufficient to detect the sub-millimeter alignment necessary to create walls that maintain structural integrity over decades or centuries. Yet the surviving walls stand, often for centuries without mortar, through earthquakes, frost, and erosion.
This is a second instance of the same pattern observed in Egypt. Different environment, different society, different material constraints, yet the same question emerges. How was measurement verified, maintained, and applied to produce a result that appears to exceed the expected precision of the available tools? In both cases, the builder's work is constrained by material physics, human perception, and environmental factors. In both cases, the resulting structures demonstrate control that is measurable, repeatable,
and far more exacting than casual assumptions about technological capability would allow. It is also important to note that Inca precision operates at a local rather than a global scale. There is no evidence of continent-spanning alignment, of astronomical or geodetic networks like those invoked for Egypt. Yet the principle remains identical, controlling geometry to a degree that is hard to explain purely with the tools documented in the archaeological record. The context shifts, the expression changes, but the underlying engineering fact persists. In both cases, the implication is profound. It suggests that human societies, operating independently and without shared knowledge, discovered methods for controlling geometry with astonishing fidelity. These methods were not documented in ways that survive to the present, and the results exceed what modern engineers would predict given the known constraints. That is the measurable contradiction. The structures do not match the expected performance of the tools. The Andes and the Egyptian desert are worlds apart in environment, culture, and material. Yet in both places, stone records an outcome that defies casual expectation. Accuracy exists where tools should not allow it. Control exists where instruments are absent. Human ingenuity appears constrained only by the mind, not the tools themselves. The Inca walls remind us that precision is a human achievement, not a technological one alone. It can emerge from careful observation, iterative correction, and an intuitive understanding of geometry, just as it can from advanced instrumentation. The method may differ, but the result is comparable. Measured outcomes exceed assumed capability. And so the question returns, shifted but familiar. A different continent, a different culture, different stone, and a different method. Yet the same core problem appears. How was this precision achieved? How was it verified? How was error controlled? The tools we can see do not fully explain it, and the walls themselves silently insist that something more subtle, more disciplined, must have been at work. The question returns in sharper focus. How do you check a fit you cannot measure? Across the Andes, the Inca achieved walls that seem impossibly tight. Stones pressed together with gaps so narrow that modern blades cannot enter them, angles maintained across multiple faces, surfaces nearly planar to the eye. Yet the tools at hand, the hammer, the chisel, the eye itself, cannot quantify flatness or alignment to the sub-millimeter accuracy that the stones display. The problem is not creating the stone, it is verifying it. Planarity is deceptively simple in concept. A flat face is one that lies on a single plane, every point equidistant from an imaginary reference surface. On a table or a small workbench, planarity can be judged by straight edges or surface plates. Small deviations are detectable by touch or sight. Scale that up to stones weighing multiple tons, some irregularly shaped, and the task becomes orders of magnitude harder. A single bump or depression of a few millimeters can compromise the fit. Yet Inca stones show no such compromise across surfaces that run meters in length. Angle consistency compounds the challenge. Each stone has multiple faces, each of which must mate precisely with neighboring stones. An angular deviation in one stone affects the entire network. Unlike a simple rectangle, the polygonal masonry of Sacsayhuaman does not allow repetitive, identical shapes. Each stone is custom-fitted. Builders must ensure that the angles of contact correspond not just locally, but in aggregate, to maintain wall stability and cohesion. Any misalignment propagates, yet the surviving walls are remarkably stable. How was this accomplished? Scholars have proposed several hypotheses. The most common is iterative fitting. In this scenario, stones are roughly shaped, set in place, then repeatedly adjusted, hammering, grinding, or chiseling until the fit is perfect. This method can, in principle, produce extremely tight joins. It relies on patience, skill, and the ability to perceive contact across multiple points. It also requires a feedback system, some way to know whether adjustments are improving or worsening the fit. Another proposed method is the transfer of angles. Builders could have used physical templates or reference stones to carry an angle from one location to another. By placing the template against a stone already in position, the next stone could be shaped to match. This introduces a form of indirect measurement. Rather than measuring the angle numerically, they compare it relationally. Each stone becomes both a target and a reference, creating a network of interdependent geometry. These methods are plausible at a local scale. They can produce tight joins between adjacent stones. They can approximate planarity and alignment through repetition and feedback. Yet they strain under scrutiny when extended to large walls. Error compounds, as in the Egyptian case. Small misjudgments in a single stone create deviations in the next. If there is no independent way to measure absolute alignment, the system relies entirely on relational consistency. The walls suggest that the method worked, but the precise mechanism remains opaque. One limitation of iterative fitting is human perception. The eye can detect misalignment to a certain limit, but millimeter-level deviations over several meters challenge even trained vision. Touch and tactile feedback help, but stones of several tons cannot be adjusted with the precision of a handheld tool without careful staging. The time and labor required would be immense, yet the construction sequence implies efficiency. Another strain arises in cumulative angle transfer. Moving a geometric relationship from one stone to the next introduces uncertainty. Without a global reference, there is no absolute check. The result could drift subtly over dozens of stones, yet surviving walls show uniformity in fit and angle. How was drift prevented? How was consistency maintained across a sequence of interlocking stones without measurement instruments capable of detecting millimeter or arc-second level deviations? Environmental factors complicate the picture further. Stones are not uniform in density or hardness. Thermal expansion, moisture absorption, and micro-defects can affect how one stone sits against another. Without numerical measurements, any control must be encoded in method, processes that inherently compensate for these variables through sequence, observation, and adjustment. Despite these challenges, the evidence indicates success. Contact surfaces are nearly perfect, joints are minimal, angles are consistent. The outcome behaves as if there were a system of checks, not necessarily instruments, but procedures that ensure error does not accumulate beyond tolerable limits. The builders created a form of implicit verification, where the geometry itself acts as the measuring device. Stones reference each other. Fit provides feedback. The wall enforces its own standard. This realization is critical. It shows that measurable engineering fact does not always require numerical measurement in the modern sense. Verification can be relational, iterative, and embedded in the process. Yet even this explanation has limits. There is a threshold where relational checks become insufficient to guarantee uniformity across large surfaces or multiple levels of construction. Sacsayhuaman approaches that threshold. Its surviving precision still strains our understanding of what could be achieved with the documented methods alone. The problem becomes even more striking when we shift continents again. If the Andes present a version of this contradiction at a local, adaptive scale, what happens when similar precision appears in another culture, in another environment, with another set of constraints and tools? The pattern of achievement is repeated, yet the context is different. The same question, how was precision verified, maintained, and controlled without instruments, emerges anew. And so the mind turns eastward, toward Cambodia, where stone again speaks of engineering control that appears to exceed documented capability. The polygonal walls of the Andes are not unique in their challenge. They are part of a broader pattern, a persistent question that crosses geography, culture, and material. The methods may differ, the materials may differ, the scale may differ. Yet the measurable engineering fact, the observed precision, forces the same paradox. The outcome exceeds what the assumed tools and techniques should allow. The inquiry now deepens. If the Andean builders relied on relational, iterative methods, How do those methods compare to what we find in the temples of Angkor? Can the principles of fit, verification, and angle control illuminate another independent culture? Or does the Cambodian example demand a wholly different explanation, one that converges on the same uncomfortable truth? That human societies, separated by thousands of kilometers and centuries, repeatedly solved problems of precision in ways that defy straightforward reconstruction from the tools we can see. The evidence invites the question without offering an answer, and that question is waiting, quietly insistent, in the heart of Cambodia. In the lowlands of Cambodia, where the Tonle Sap floods the surrounding plains seasonally, the Khmer Empire laid out a monumental city that continues to baffle engineers and historians alike. Angkor Wat, the jewel of this civilization, is not a single building but an entire complex, a deliberate imposition of order on the tropical landscape. Unlike the tight polygonal masonry of the Andes or the near-perfect right angles of the Giza Plateau, Angkor exhibits a different expression of control, modular geometry at an urban scale, precise enough to coordinate construction over kilometers of temples, reservoirs, causeways, and roads. From the outset, the design of Angkor Wat demonstrates careful planning. Archaeologists have identified grid-like patterns underlying the layout, with axes aligned to cardinal directions, terraces following systematic elevation changes, and basins and canals arranged in functional symmetry. The main temple sits at the center of a series of concentric enclosures, oriented along a north-south axis, and carefully proportioned so that approach, elevation, and sightlines align. The orientation is not perfect to the degree of a few arcseconds, as seen at Giza, but it is controlled at a scale that dwarfs even monumental pyramids. Large embankments are leveled to within tens of centimeters, causeways maintain straight trajectories over hundreds of meters, and the modular dimensions of stone blocks and foundations repeat with consistent ratios. This modular system is significant. Each component, temple, gallery, reservoir, was designed to fit within a larger geometric network. Builders did not rely solely on visual approximation. Instead, they translated measurements across space using reference lines, axes, and proportional units. Evidence suggests a unit of measure was applied consistently, allowing builders to scale designs accurately without needing absolute angular measurement at every step. This created a form of relational precision, a system in which one reference point could propagate geometric consistency across a sprawling site. The engineering challenge here is subtle but profound. Control at this scale requires coordination across multiple teams and multiple sites simultaneously. Unlike the Andes, where each wall is self-contained, or Giza, where a single base governs the pyramid, Angkor involves a network of structures that must maintain relative alignment and proportion over kilometers. Small deviations in one area could cascade into misalignments elsewhere. The Khmer accomplished this by enforcing a modular system, repeating dimensions, applying standardized reference axes, and using modular blocks of stone that implicitly encode alignment. Surveying techniques at Angkor were necessarily practical. There is evidence that plumb lines, water leveling, and simple sighting methods were employed. For example, embankments and reservoirs show leveling within a few centimeters over hundreds of meters. Straight causeways suggest repeated visual alignment and the use of ropes or poles to maintain direction. These methods, like those in Egypt or the Andes, are straightforward in concept, but limited in precision. Yet the cumulative effect produces a coherent geometry that spans an enormous area. One of the most fascinating aspects is how local variations in terrain were integrated. The Khmer did not impose a rigid orthogonal grid on a landscape of rivers, swamps, and seasonal floodplains. Instead, they adapted modular geometry to the environment, adjusting measurements and orientations to maintain relative consistency while compensating for uneven ground. The result is not perfection in the modern sense, but a disciplined application of proportional and geometric rules that produces controlled, harmonious scale. When compared to other civilizations discussed earlier, Angkor represents the same core engineering problem reframed. In Egypt, precision manifests in tight right angles and base leveling over hundreds of meters, demanding extraordinary control of angular error. In the Andes, precision appears as near-perfect planarity and interlocking of irregular polygonal blocks, creating stability without mortar. At Angkor, precision is encoded in modular repetition, geometric ratios, and alignment of a sprawling urban plan. The problem is consistent across all three contexts. How do independent civilizations maintain control of geometry over large distances using only basic tools and empirical methods? The Khmer employed what might be called indirect verification. Instead of measuring angles or distances with high-precision instruments, they transferred geometry relationally. A grid line for a causeway could be laid out using sighting poles, then extended using proportional units derived from standardized modules. If a building did not conform to the expected module, adjustments could be made in subsequent placements. This method functions like a feedback system, not by quantifying error numerically, but by encoding constraints into the construction process. Each completed structure validates the system for the next, producing large-scale consistency without the need for arc-second measurement. The modular approach also mitigates the error stacking problem that dominates high-precision endeavors. By using repeated units and proportional relationships, minor deviations in one module do not propagate catastrophically. Instead, the network is self-correcting. Discrepancies are absorbed or averaged out over multiple iterations. It is a different solution to the same underlying challenge that Egypt and Peru illustrate: managing error and maintaining control over geometry at a scale that surpasses naive expectations based on known tools. In analyzing Angkor, it becomes clear that technological sophistication is not the only route to precise outcomes. The Khmer relied on organizational control, modular planning, and geometric logic. The outcome is measurable. Causeways run straight for hundreds of meters, temples maintain proportionality, enclosures maintain alignment, and water management systems function reliably within centimeters of intended grade. These are not artistic approximations. They are engineered results, produced without instruments that modern engineers would consider necessary for such scale. Moreover, the Khmer solution is independent. There is no evidence of knowledge transfer from Egypt or the Andes. The approach is culturally and geographically distinct, yet it resolves the same fundamental problem: how to impose large-scale geometric control with empirical low-tech tools. The pattern repeats: civilizations separated by millennia and thousands of kilometers converging on measurable control over geometry that exceeds assumed technological capability. The contrast also reinforces the theme of diversity in approach. Giza demonstrates precision in angles, the Andes in local fit and interlocking, and Angkor in large-scale modular alignment. Each method is suited to the material, environmental constraints, and societal needs of its context. What unites them is the measurable engineering fact. The achieved outcome exceeds what the documented tools and methods suggest should have been possible. Independent societies solved the same abstract problem, but arrived at solutions tailored to their circumstances. At Angkor, the geometric control is both subtle and profound. There are no right angles measured to arc seconds. There are no perfectly interlocking polygonal stones. Instead, there is a network of references, modular units, and proportional constraints that maintain large-scale consistency across kilometers. The success is evident not in isolated measurements, but in the coherence of the city as a whole. The plan works, the structures endure, the water flows, the causeways remain aligned. The evidence challenges assumptions about technological capability. When modern engineers examine Angkor, they see an achievement that could only arise from a sophisticated understanding of geometry, planning, and construction sequencing. Yet the tools at hand, ropes, poles, water, and simple sighting, cannot account for the observed consistency unless they are applied within a disciplined system that implicitly encodes verification and feedback. As with Giza and the Andes, the stones themselves testify to controlled outcomes that exceed naive expectations. And so the recurring question returns. Is this convergence, the repeated appearance of measurable geometric control across independent civilizations, evidence of a universal problem-solving logic inherent to human construction? Or is it coincidence, a remarkable alignment of intention, experience, and circumstance that produces similar outcomes without shared knowledge?
Angkor Wat stands as a final testament to a different approach. It is not perfection in the narrow sense, but it is precise, consistent, and scalable. It is a solution to the same engineering challenge that Egypt and Peru present, imposing reliable geometric order over space using empirical methods. The Khmer demonstrate that there is more than one way to control geometry. The outcome remains measurable, real, and, by any modern standard, impressive.
Across continents and cultures, a pattern emerges. Independent societies repeatedly arrive at solutions to the problem of maintaining geometric control at a scale and precision that defies simple reconstruction from the surviving tools. Each solution is contextually adapted, yet the underlying challenge is the same: verification, error control, and the creation of geometry that exceeds assumed technological limits. And with Angkor, the circle widens. Giza showed control through right angles, the Andes through interlocking fit, Cambodia through modular planning. The measure of achievement is different, but the principle is identical. Across disparate landscapes and times, human societies confronted the same problem, and in each case, produced results that speak to ingenuity, discipline, and an understanding of geometry that continues to challenge modern expectations. The question lingers: how did these civilizations consistently produce measured outcomes that their tools, by themselves, should not have allowed? Convergence or coincidence, independent solution or universal principle, the evidence demands we consider the possibility that humans, everywhere, have repeatedly discovered ways to impose control over space and matter that exceeds our intuitive assumptions. And it is here, at this midpoint of the journey, that the true pattern becomes visible. 3 continents, 3 civilizations, 3 approaches, all producing results that defy the limits suggested by documented instruments. The problem is real, the outcomes are measurable, and the contradiction remains. Across centuries and continents, a curious pattern emerges. In Egypt, the pyramid bases exhibit angular deviation measured in mere arc-seconds. In the Andes, Inca walls interlock with millimeter-level precision. In Cambodia, the Khmer imposed modular grids with consistent large-scale geometry. These are independent civilizations, separated by thousands of kilometers and millennia, working with different materials, tools, and cultural priorities. And yet in each case, a measurable engineering outcome exceeds what is expected given the known technology. The natural question arises: is this coincidence? Could it be that despite their independence, these societies simply happen to achieve precision that seems improbable to modern observers? To answer, we must step away from romantic notions and examine probability through the lens of mathematics and engineering constraints. In statistical terms, the likelihood of independent emergence of such precision can be modeled by considering the expected variance imposed by the documented tools and methods. For example, if a rope stretched under tension introduces errors on the order of centimeters over hundreds of meters, and human perception adds arc-minute uncertainties, then each independent measurement carries an expected deviation. Cumulatively, over multiple measurements or constructions, the distribution of outcomes spreads further. To achieve arc-second level accuracy across a base more than 200 meters long, as in Giza, is to reach into the extreme tail of that distribution. Similarly, Inca walls require iterative shaping of stones so that adjacent surfaces meet within millimeters. Each fitting carries an inherent tolerance due to material irregularities, human error, and environmental factors. The probability that dozens of massive stones fit together across a wall without detectable gaps using only hand tools and eye judgment, is extremely low if approached as a random process. Repeat that outcome independently in multiple walls across various sites, and the likelihood of pure chance becomes vanishingly small. At Angkor, the situation is slightly different but no less remarkable. The modular planning and proportional consistency across kilometers of causeways and temple complexes imply adherence to a geometric system that maintains relative alignment despite terrain variability. Without standardized instruments, deviations should accumulate, yet they remain constrained. The probability of achieving this level of order through ad hoc, uncoordinated measurement is likewise extremely low. When considering probability in this context, it is crucial to distinguish between random chance and engineered outcomes. Random chance would imply outcomes distributed according to the expected error ranges imposed by tools and human limitations. Engineered outcomes, by contrast, emerge when processes are applied deliberately, using methods that reduce error, verify results, and compensate for environmental and material variability. The data suggests that each of these civilizations employed methods that behave like engineered processes. The frequency of near-perfect results far exceeds what we would expect from random variation alone. Statistically, it is not impossible that such precision could emerge by chance, but the odds are extraordinary. For each civilization, the probability of achieving these measured outcomes using the tools at hand, without some form of feedback or verification, is extremely low. Combine 3 independent occurrences across the globe, separated in space and time, and the likelihood of coincidence drops to near zero. This leads to a subtle but critical point. Our perception of improbability is grounded in the assumptions we make about tool limitations, human capability, and environmental interference. When we treat the tools as defining the absolute ceiling for precision, the outcomes appear contradictory. But if the tools are combined with disciplined methods, implicit feedback mechanisms, and process-oriented verification, the probabilities shift dramatically. The measured results are no longer statistical anomalies. They become plausible, though still remarkable. Engineering constraints help clarify the context. Each system, whether pyramid, wall, or temple complex, is constrained by material properties, environmental factors, human ergonomics, and measurement error. These constraints define the space of possible outcomes. Achieving consistent results within that space requires processes that actively manage variance. Repetition alone cannot account for the level of consistency observed. Some method of error suppression, feedback, and relational verification is necessary. The repeated emergence of such outcomes across independent cultures strongly suggests that similar problem-solving strategies were discovered organically rather than coincidentally. It is also worth considering the role of scaling. Small-scale precision is intuitive and achievable with basic tools. Large-scale precision, particularly when compounded over distances or complex geometries, magnifies errors and magnifies the consequences of minor deviations. The fact that all 3 civilizations managed to constrain error effectively at significant scales reinforces the argument against coincidence. This is not luck, it is method applied consistently. Probability theory further sharpens the contrast. Suppose each independent measurement or fitting has a probability of success based on tool limitations and human perception. Even modest probabilities, compounded across dozens of measurements, reduce the likelihood of achieving high precision to infinitesimal levels. The measured outcomes we observe, arc-second deviation at Giza, millimeter gaps in Peru, kilometer-scale alignment in Cambodia, occupy the extreme tail of that distribution. The coincidence of 3 independent outcomes occupying the tail simultaneously is statistically implausible. This forces the question, if coincidence is unlikely, what remains? The alternatives are methodological. Either the civilizations developed procedures that functioned as implicit verification systems, allowing them to control geometry beyond naive expectations of their tools, or our assumptions about the limitations of those tools are incomplete. It may be that techniques existed that are no longer documented, Techniques that amplified the effectiveness of basic instruments, relied on relational geometry, or leveraged environmental constants like celestial observation and water leveling in ways not fully appreciated. The distinction is crucial. We are not invoking mysticism, lost civilizations, or unrecorded technology in the sense of advanced devices. We are observing measurable, verifiable outcomes and contrasting them with documented limitations. The contradiction is real. The statistics make clear that pure chance cannot plausibly account for the precision. What remains is human ingenuity expressed through methods we may not fully reconstruct. And yet, probability alone cannot explain the repeated convergence. It highlights the anomaly, but does not reveal the mechanism. The paradox is not in the results. It is in the gap between the documented tools and the measured outcomes. Every calculation of expected error emphasizes the improbability. Every observation of surviving structure confirms that improbability was overcome. The solution must lie in process, method, or understanding that was embedded in construction practice rather than in instruments themselves. So, the problem is reframed. The contradiction may not be in the civilization's ability to produce precision, but in our assumptions about how measurement and verification must occur. We assume that without modern instruments, angular and geometric control beyond certain thresholds is impossible. The evidence suggests otherwise. Across continents and millennia, human societies repeatedly exceeded the constraints we impose on them, using the tools available, guided by empirical methods, observation, and iterative correction. This is where probability intersects with engineering logic. The odds of coincidence are infinitesimal. The measurable outcomes demand explanation rooted in method. The contradiction is not supernatural or mysterious. It is statistical and procedural. It is an invitation to rethink assumptions about what constitutes sufficient verification and about the ways human ingenuity can manipulate space, geometry, and material to achieve measurable precision. And with that realization, a new question emerges. If the contradiction lies not in the results but in our assumptions, then what have we been missing when we judge the limits of ancient engineering? How does this reshape our understanding of what is possible when human skill, observation, and iterative method combine over time and scale? Modern engineers approach these ancient constructions with a mixture of admiration, frustration, and cautious respect. When surveyors, structural engineers, and architects examine the base of the Great Pyramid, the polygonal walls of Peru, or the modular layouts of Angkor, they often begin with a simple question: how would we reproduce this today? The answer is illuminating, because it clarifies the gulf between capability and expectation. Surveyors immediately focus on measurement. To replicate a right angle across 230 meters with an error of only 12 arc-seconds would require tools that provide feedback far beyond what the Old Kingdom documented. A modern team would deploy optical theodolites capable of resolving angular differences in seconds of arc, or total stations that combine electronic distance measurement with precision angular readings. Distances would be surveyed with laser scanners or steel tapes under strict tension, environmental factors recorded and compensated, and each corner repeatedly checked from multiple reference points. Even with such instrumentation, the task is delicate, time-consuming, and demands continuous monitoring. Possible, many engineers note, does not mean easy. Structural engineers focus on fit and stability. They consider the Inca walls, where polygonal stones interlock with sub-millimeter accuracy. Modern masons attempting to replicate this level of interlocking would need controlled workspaces, pre-shaped stones, and repeated trial fitting. Every piece would require careful adjustment, with constant measurement to prevent cumulative error. Without advanced tools, maintaining consistent planarity and angle across dozens of massive blocks becomes an almost Sisyphean endeavor. Engineers admit that the end product is achievable in principle, yet extraordinarily labor-intensive and dependent on iterative verification. At Angkor, urban planners and civil engineers note the large-scale modular consistency. Causeways, reservoirs, and temples align over kilometers with tolerances that are tight by the standards of terrain and construction materials. Today, engineers would rely on survey networks, GPS references, laser leveling, and standardized units. They would model the site digitally, calculate error propagation, and maintain precise records throughout the construction sequence. Without such instruments, achieving comparable alignment and proportional consistency over this scale is considered exceedingly difficult. The repeated theme in these assessments is humility. Engineers do not question the measurements themselves, they accept them, but they recognize the challenge. The structures are not merely impressive artifacts of artistry or labor. They are precise functioning systems that demonstrate an understanding of geometry, feedback, and process that rivals modern expectations. The documented tools of these civilizations, ropes, plumb bobs, merquettes, water levels, do not, on their own, explain the outcomes. There is a silent concession. Skill alone, while extraordinary, is insufficient to account fully for measured accuracy. Engineers make an important distinction. To say a result is possible is not to claim it is trivial. The Great Pyramid could theoretically be constructed today with the tools and methods documented for its time, but the labor, time, and careful process required would be immense. The same applies to Inca walls and Angkor Wat. Explained does not mean demonstrated. Archaeologists can hypothesize methods and propose iterative fitting, transfer of angles, or modular measurement systems. Engineers can calculate tolerances and model error propagation. Yet no one has fully demonstrated, in controlled experiments, the precise process that achieves the observed results consistently across the same scales. Modern surveys reinforce the mystery. Remeasurements of the Great Pyramid reveal base leveling to within plus or minus 2 centimeters over 230 meters and angular deviation of only 12 arcseconds. Inca walls, once surveyed carefully, show gaps of less than a millimeter between massive stones. At Angkor, modern mapping demonstrates proportional consistency across kilometers of causeways and temples. These measurements are not guesses. They are empirical, repeatable, and confirmed independently. Engineers acknowledge that these results exist in a category that exceeds casual capability. The implications of these assessments are subtle but profound. Engineers recognize that the ancient methods likely involved some combination of observation, iterative adjustment, and relational verification. They accept that it is feasible to achieve extreme precision with simple tools, but only if procedures are disciplined, feedback is continuous, and human error is constantly corrected. In essence, ancient builders may have been performing engineering experiments over long durations, where the structure itself became the measuring instrument, revealing inconsistencies as construction progressed. Yet there is caution in the tone. Engineers rarely claim certainty about method. Experimental archaeology and reconstruction projects attempt partial demonstrations, but reproducing the exact outcomes of Giza, Sacsayhuaman, or Angkor remains beyond reach. This admission is instructive. The gap is not in imagination, willpower, or modern knowledge. It is in the documented method. The results are reproducible conceptually but not demonstrated empirically with the same tools at the same scale. That gap between documented capability and measured outcome is precisely where the tension resides. Surveyors emphasize redundancy as a principle. When building large-scale projects today, multiple independent measurements, cross-checking, and iterative correction are essential. Ancient builders could not measure angles with electronic theodolites, but the principle may have been recognized intuitively. Check and recheck, compare relative positions, use existing structures as reference points. The engineering insight is that measurement is not just about tools, it is about process, feedback, and relational geometry. The remarkable precision seen in these constructions suggests that such principles were applied rigorously. Another point modern engineers highlight is the role of material physics. Massive stones behave predictably under compression, yet small differences in placement can alter stress distribution. The Inca walls, for example, demonstrate a sophisticated understanding of how irregular stones interlock to distribute force and resist seismic activity. Engineers note that even with modern tools, achieving similar interlocking efficiency requires careful consideration of weight, center of gravity, and contact surface. The ancient builders appear to have integrated these factors into their geometric planning intuitively or empirically. In contemporary terms, what engineers observe is a convergence of skill, method, and environmental intelligence. The tools themselves, the ropes, plumb bobs, and simple sighting devices, provide limited resolution. But disciplined use of these tools, coupled with relational verification, iterative fitting, and perhaps modular systems, amplifies their effectiveness. The outcome is measurable, precision that seems beyond the limits imposed by the instruments alone. This perspective reframes the discussion. The question is not whether the ancients were capable, it is not whether the results are credible. The question is how methodology, skill, and process combine to achieve results that remain, even by modern standards, impressive. Engineers can model, estimate tolerances, and replicate aspects of the construction, but they rarely replicate the exact process with the same resources and constraints. That is the measure of the anomaly. The known instruments as documented should not, in theory, produce outcomes of this consistency at such scale, yet they do. And so engineers become, in a sense, mentors to the inquiry. They provide the framework for understanding what is feasible, what is expected, and where contradictions appear. They quantify the improbabilities, model the propagation of error, and translate archaeological observation into technical terms. Their quiet admissions, the acknowledgement that possible is not easy and explained is not demonstrated, illuminate the gap between expectation and reality. It is a gap that defines the core paradox of ancient precision. These reflections prepare the way for the next stage of inquiry, empirical demonstration. Theory, calculation, and modern replication projects can illuminate possibilities, but the ultimate proof lies in the act of building or reconstructing under constraints comparable to the original. Only then can one determine whether the measured outcomes were a product of extraordinary iterative skill, relational geometry, modular verification, or some combination thereof. Until that step is taken, the contradiction between documented tools and observed precision persists as an engineering fact, tangible, measurable, and inescapable. And so the narrative turns to experimentation, to the act of testing assumptions in controlled conditions. Demonstrations matter. Without them, the discussion remains theoretical, bounded by probability and inference. With them, it moves into the tangible realm, where the limits of method, the capabilities of human ingenuity, and the consequences of scale can be observed directly. The next stage will confront that challenge. Can measured outcomes be replicated with known tools, and if so, how? The engineer's perspective has set the stage. The answer now depends on controlled observation, rigorous methodology, and the patient trial of hypothesis against reality. Modern experimental archaeology has sought to bridge the gap between theory and practice, to test in a controlled way what ancient builders could realistically achieve with the tools documented in history. Across continents, researchers have attempted to recreate aspects of Egyptian, Andean, and Khmer construction with varying degrees of success. The effort is not casual. It requires careful measurement, skilled labor, and patience measured in months or even years. The results are illuminating, yet in nearly every case, they reveal both the potential and the limitations of known techniques. In Egypt, attempts to reconstruct sections of pyramid bases using ropes, plumb bobs, and leveling instruments such as water trenches provide a telling case study. Teams can achieve right angles that are visually convincing and even measure within a few arc minutes of perfection over short distances. Yet when scaled to the full length of the base, hundreds of meters, the cumulative error becomes apparent. Minor deviations in alignment or leveling propagate across corners, introducing discrepancies that exceed those documented at Giza. Researchers often remark that human perception alone is insufficient to maintain the necessary consistency. Without instruments that provide feedback in arc seconds, it is difficult, even for modern engineers following documented methods, to replicate the exact precision. In the Andes, replication attempts focus on polygonal masonry. Teams working with hand tools can fit stones tightly, sometimes achieving millimeter-level gaps over single joints. However, sustaining that precision across multiple stones, each uniquely shaped and weighing several tons, proves extremely challenging. Many experiments resort to pre-shaping stones in controlled conditions or making repeated adjustments over days, illustrating just how labor-intensive the process would have been. Even so, perfect replication remains elusive. Gaps slightly larger than those in Sacsayhuaman often appear, and subtle angular deviations accumulate. These results underscore the improbability of achieving the measured precision without a highly disciplined iterative system, feedback loops, or techniques that are undocumented in the archaeological record. At Angkor, modern reconstructions of modular layouts demonstrate a similar pattern. Researchers attempting to recreate causeways, temple foundations, or waterworks can follow geometric grids and proportional systems with basic tools. They achieve reasonable alignment and repeatable ratios, particularly over tens of meters. Yet as scale increases to hundreds or thousands of meters, slight deviations compound. Subtle errors in leveling or orientation emerge, despite careful observation. The controlled replication highlights the efficiency of modular planning as a method for error mitigation, but it also reinforces the paradox. The Khmer achieved large-scale consistency far exceeding what simple empirical methods seem capable of producing. A common thread emerges across these experiments. Approximation is possible, equivalence is rare. Builders and experimental teams can produce outcomes that look correct from a distance, and they can match local measures of planarity or alignment reasonably well. But the extreme precision recorded in surviving structures, the 12 arc-second deviation of pyramid bases, millimeter-level interlocking of Andean stones, kilometer-scale proportional alignment in Angkor, is generally beyond replication with the documented tools alone. Even with modern supervision and careful measurement, errors tend to accumulate. Researchers note that repeated fitting, careful observation, and iterative correction can partially compensate for tool limitations, but doing so requires an extraordinary level of attention, time, and coordination. In experimental trials, teams often exhaust labor and resources long before achieving the consistency evident in the archaeological record. The implication is clear. The ancients employed methods that incorporated error checking and verification in ways that are not fully documented or understood. The process was effective enough to produce structures whose measured precision challenges modern expectations. These findings are reinforced by surveys and measurements taken during replication attempts. Even when teams are allowed to pause, adjust, and double-check every step, measured errors in modern trials exceed those in the original constructions. This emphasizes a recurring theme. The contradiction is not in human capability, but in the combination of tools, method, and scale. The surviving structures display consistency that cannot be explained solely by chance or by the basic tools in use. There is a method at work, but its exact mechanics remain partially opaque. Experimental archaeology also highlights the importance of implicit knowledge. In every trial, teams learn that success is not only about measurement, it is about sequence, relational verification, and adaptation to subtle irregularities in stone or terrain. Each stone, each module, each foundation serves as a reference for the next. Feedback is embedded in the work itself. When a block does not fit, the builders adjust either the block or the surrounding stones until conformity is achieved. This observation aligns with previous engineering analyses. Error propagation is managed through relational, iterative processes rather than numeric measurement alone. Yet the speed and efficiency of the ancient executions remain unmatched in modern experiments, suggesting a level of practical mastery that we can observe but not fully replicate. At Giza, the experiments underscore the sheer difficulty of scaling precise right angles across hundreds of meters. Teams using ropes and sighting sticks can maintain an approximate right angle, but arc-second deviations are nearly impossible to achieve consistently without modern surveying tools. This pattern echoes in the Andes, where achieving millimeter-level interlocks over dozens of stones defies replication without extensive trial-and-error procedures. And at Angkor, recreating kilometer-scale alignment reveals that minor local adjustments are necessary to maintain global proportional consistency, but even the smallest miscalculation leads to cumulative deviation. Taken together, these experiments reinforce the central paradox. The outcomes, arc-second pyramid corners, perfectly interlocking stones, and modular urban geometry, exceed what documented tools and methods should allow. Modern replication demonstrates feasibility in principle, but practical equivalence is rarely achieved. It is as if the ancient builders had a combination of skill, observation, and method that we can understand conceptually, but cannot fully reproduce under the same constraints. This leads inevitably to a deeper question. If approximation is achievable but precise equivalence remains elusive, what are we missing? Are there subtle techniques, unrecorded processes, or procedural insights that amplified the effectiveness of basic instruments? Were methods encoded in iterative routines, relational geometry, or collective feedback that allowed error to be controlled and minimized at scales we struggle to manage today? The experiments leave us with tangible results and measurable discrepancies. They confirm that the engineering feats of Giza, the Andes, and Angkor are not products of luck or mysticism. They are the outcome of disciplined, repeatable, and extraordinarily skillful processes. Yet they also confirm that our understanding of those processes is incomplete. The gap between approximation and exact replication emphasizes the paradox that defines these constructions. The measured precision exists, the documented tools cannot fully account for it, and modern trials struggle to reproduce it. It is in this space between achievement and understanding that the inquiry deepens. Every experiment teaches us what works, where errors accumulate, and how skill can partially overcome limitations. Every failure highlights the areas where ancient methods must have been more sophisticated than the surviving records suggest. And every approximation draws attention to the difference between what is physically possible and what is documented, measurable, and demonstrable. So the question lingers, pressing and unavoidable. What are we missing? The experiments tell us much, but they do not close the gap. They reveal the method's limits, the constraints of human perception, and the boundaries imposed by scale and material. Yet they also affirm the reality of the outcomes themselves, measured, verified, and enduring. Somewhere within these trials, within the intersection of method, observation, and iteration, lies the solution, an understanding of precision that was encoded in process, not in instruments alone. The evidence compels us to confront a fundamental truth. We may comprehend the principles conceptually, but without the exact procedural knowledge, the results remain out of reach. And in that gap, the contradiction persists. The ancient achievements stand, the modern experiments fall short, and the question remains: what is the method that enabled humans, across continents and centuries, to achieve measurable precision that defies simple reconstruction? Across the record of ancient construction, a persistent tension emerges between what can be calculated and what can be executed. The mathematician, the engineer, or the architect may understand in abstract terms how to produce a right angle, a straight line, or a proportional system. Formulas, ratios, and principles can be articulated on papyrus, etched into stone, or transmitted orally. Yet the translation of that knowledge into physical reality, the act of turning geometric theory into stone, earth, and timber, requires a distinct set of competencies, a form of tacit knowledge that rarely survives beyond the laborers, artisans, and overseers who wielded it. In the context of the Great Pyramid, we can quantify what is mathematically necessary to produce a 90-degree corner across 230 meters with an error of only 12 arcseconds. The geometric relationships are straightforward to an engineer: the slope of each side, the perpendicular intersection at the base, the leveling of the foundation. Calculations of deviation, error propagation, and compensatory adjustments can be performed with pen, paper, or even computational tools. In theory, one could outline step by step what the builders must have done. Yet in practice, converting this theory into precise action is an entirely different problem. Practical implementation introduces countless variables: material properties, environmental conditions, human error, and tool limitations interact in complex ways. Ropes stretch unpredictably depending on humidity. Plumb bobs swing in the wind. Stones vary in density, size, and shape. Even if a plan exists for how to set a corner, the act of actually doing it introduces subtle deviations. Each adjustment, each hammer strike, each sighting requires judgment honed through repeated experience, not simply knowledge of geometry. The skilled eye and practiced hand become instruments of measurement in themselves. Without this tacit understanding, even perfect calculations will fail to produce the observed precision. Tacit knowledge is difficult to quantify. It encompasses learned intuitions, procedural memory, and empirical insight embedded in practice rather than written text. In the Andes, for example, the fitting of polygonal stones was not a mechanical process. It was a system of perception and manipulation. The masons understood how stones would settle under gravity, how contact points would transmit force, how micro-adjustments in placement would propagate through the structure. These are skills that are acquired through apprenticeship, repetition, and a kind of embodied understanding that does not translate easily into diagrams or manuals. When modern teams attempt replication, they can follow guidelines, yet the subtleties of stone behavior, force distribution, and tactile feedback often escape them. At Angkor, the translation from modular plan to executed construction required a similar type of tacit knowledge. Builders had to adjust proportional units for terrain irregularities, maintain relative alignment over kilometers, and coordinate teams working simultaneously on different parts of the complex. Knowledge of proportional scaling, measurement transfer, and error absorption had to be internalized. Even when grids and axes were laid out, the practical act of maintaining alignment depended on iterative correction and constant observation, procedures that likely relied on skill systems passed down orally or through apprenticeship rather than recorded formulas. The gap between knowing and doing is amplified by scale. A single stone, a short wall, or a small temple can be adjusted with direct measurement and careful observation. Errors are localized and manageable. As scale increases, hundreds of meters for a pyramid base, tens of meters for Inca walls, kilometers for Angkor causeways, small deviations accumulate. At that scale, the translation of abstract knowledge into actionable procedure becomes exponentially more complex. Each step depends not only on understanding geometry, but on anticipating error, propagating correction, and coordinating human effort. Tacit knowledge functions as the control system, distributing expertise across the team, translating observation into adjustment, and encoding verification into every movement.
Importantly, this process was not necessarily documented. The Egyptians left some mathematical texts and measurement instruments, the Incas left no known written system for geometric transfer, and the Khmer left inscriptions and plans that reveal intent more than method. What survives is the result, not the procedural record. The builders themselves carried understanding in the form of apprenticeship, repetition, and experience. Once those practitioners are gone, the precise system of tacit knowledge disappears as well. We see the outcomes, measure their precision, and are left to reconstruct the processes through experiment, simulation, and inference. This distinction between documented knowledge and applied skill reframes the paradox. The measured precision is real. It is tangible, repeatable, and verified through surveys. What is not preserved is the procedure by which that precision was achieved. Engineers and experimental archaeologists can model, hypothesize, and attempt replication. Yet the original method remains partially invisible because it existed as tacit knowledge, embedded in practice rather than writing. The contradiction is not one of capability but of transmission. Results endure, knowledge fades. We must also separate romanticized notions of skill from technical reality. These civilizations did not possess mystical insight or supernatural ability. They operated within material, environmental, and ergonomic constraints. Their achievements are remarkable not because they were impossible in a fantastical sense, but because they demonstrate mastery of error management, relational measurement, and iterative correction. Elements of engineering practice that modern observers understand conceptually, but cannot fully reproduce without trial and refinement. Tacit knowledge amplified basic tools into a system capable of producing measurable outcomes that exceed expectations based on instruments alone. The same principle applies to the Andean and Khmer examples. Each stone, each module, each structural axis carried embedded knowledge about fit, alignment, and proportion. The mason's hands, eyes, and judgment served as both instruments and verification mechanisms. Adjustments were made incrementally, guided by experience rather than written formulas. The observed precision is therefore a product of both theoretical understanding and the disciplined application of tacit skills, a combination that is extraordinarily difficult to reconstruct once the practitioner is absent. Modern attempts at replication emphasize this gap. Teams can approximate outcomes using calculated methods, but without the original tacit knowledge encoded in practice, they fall short. Measurements may be close, surfaces may align visually, and angles may approach theoretical targets, yet the subtle refinements that ancient builders applied to achieve extreme precision over large scale remain elusive. The replication highlights the difference between knowing what should be done and executing it with the accuracy that history records. In some ways, this is a cautionary lesson about the fragility of practical knowledge. Tools and documentation can persist, results can endure in stone and earth. But the procedures, judgment, and embodied understanding that produce measurable precision are easily lost. Knowledge can disappear even when outcomes survive, leaving a gap between the technical capability implied by a structure and our ability to reconstruct it. Modern engineers, archaeologists, and masons are left to bridge this gap using inference, experimentation, and careful observation. Yet the complete method remains partially inaccessible. The paradox is thus refined. The contradiction is not merely in the tools or the skill of the builders, it is in the transmission of tacit knowledge across generations. Ancient civilizations mastered processes that allowed them to produce measurable precision, but that knowledge existed primarily in practice, not in durable documentation. Once practitioners passed, the procedures became invisible. Structures remain, precise and measurable. The human understanding that created them, however, recedes into the shadows of history. And so the journey confronts its most sobering realization. It is possible to know the mathematics of a problem, to model it theoretically, and even to approximate its solution. Yet translating that knowledge into exacting physical reality at scale requires tacit understanding that does not survive in conventional records. The result can endure for millennia, defying expectations, while the knowledge that created it quietly vanishes. In the shadow of these enduring monuments, we are reminded that skill systems, methodologies embedded in human practice, can be lost, even as the outcomes persist, leaving us to measure what we cannot fully reproduce. Knowledge can disappear, even if results remain. The question that has guided this inquiry returns with renewed force. What measurable engineering fact does not match the assumed technological capability? In every case examined,
Giza, the Andes, Angkor, the answer lies not in speculation, myth, or unrecorded devices. It lies in the tangible, verifiable outcomes. The 12-arc-second deviation across a pyramid base, the millimeter-level interlocks of Inca walls, the kilometer-scale modular alignment of Khmer causeways. These are not artifacts of luck. They are measurable, documented, and repeated outcomes that challenge assumptions about what societies of the past could accomplish with the tools at hand. The contradiction, when reframed, is no longer mysterious. It is not evidence of lost technology, secret instruments, or extraordinary external influence. It is evidence that human capability, disciplined through practice and optimized through iterative methods, exceeds what modern observers often assume. Our assumption is grounded in a linear model. The precision achievable is limited by the sophistication of documented instruments. But history demonstrates that societies found ways to extend the effective resolution of those instruments through procedure, relational verification, and collective skill. In Egypt, the Great Pyramid's base is a triumph of empirical optimization. Builders used simple tools, ropes, sighting rods, water leveling, but applied them in disciplined sequences, incorporating iterative verification that functioned as a feedback loop. Each measurement informed the next. Each adjustment refined the whole. The tools themselves were insufficient in isolation, yet combined with human skill and procedural rigor, they produced outcomes that exceed the naive expectations of technology historians. The pyramid is not a mystery of instrumentation. It is a monument to human capability applied systematically. The Andes offer a parallel in a different expression. The Inca polygonal walls, irregular yet precisely interlocking, are not the product of numerical calculation, but of an empirical understanding of stone behavior, force distribution, and iterative fitting. Each stone serves as both material and measuring device, allowing builders to refine the placement of subsequent stones. The measured precision is achieved not through mechanical instruments, but through method, observation, and skill. The contradiction arises because modern assumptions undervalue these human processes, assuming that physical measurement alone defines what is possible. At Angkor, the Khmer applied a third approach. Here, precision was scaled to the urban landscape. Alignment, proportionality, and modular repetition allowed them to manage error over kilometers. The process relied on relational verification rather than absolute measurement. The measured outcome is clear. Causeways, enclosures, and reservoirs maintain consistent geometry that exceeds what one might expect from simple tools alone. Once again, the discrepancy lies not in instruments, but in the underestimated capacity of systematic human processes. Across all three contexts, a pattern emerges. Ancient societies were not attempting perfection in the abstract, but optimizing for precision within a framework that emphasized feedback, repetition, and relational geometry. They prioritized outcomes that matter for structure, stability, and function, rather than simply creating visually impressive forms. Measurement was always a means to an end, mediated by the environment, material properties, and human skill. In effect, these civilizations achieved precision as a systemic property of the construction process, rather than as a direct output of tools. Modern assumptions often obscure this reality. When engineers or historians evaluate ancient constructions, they project contemporary expectations onto the past. High precision requires high-tech instruments, yet the evidence shows otherwise. Discipline, method, and skill systems, what might be called tacit engineering knowledge, enabled precision that modern observers might consider impossible. The contradiction dissolves when we recognize that capability is not defined solely by the sophistication of tools, but by the integration of tools with procedural rigor and human expertise. This reframing also challenges the narrative of lost technology. The focus shifts from what tools ancient societies may or may not have possessed to how they applied what they had. Rope, sighting rods, water levels, and stone chisels are mundane in isolation. When deployed in disciplined sequences, under the guidance of skilled artisans, they produce measurable outcomes that surpass expectations. The apparent contradiction is thus not a failure of historical understanding, but a failure to fully appreciate the optimization strategies employed by these societies. Consider the practical implications. Ancient builders optimized construction processes in ways we rarely prioritize today. Error mitigation was built into labor routines. Verification was integrated into each stage of construction. Modularity, proportionality, and relational geometry served as substitutes for high-precision instruments. Their priorities were functional, stable structures, aligned urban grids, enduring monuments. Perfection for its own sake was irrelevant. The measurable precision emerges as a byproduct of optimization, not a deliberate pursuit of theoretical exactness. Recognizing this transforms the way we read the past. It reframes our understanding of what human capability entails, emphasizing procedure, skill, and systems thinking rather than simply technical inventory. The ancient world was capable not because it possessed mysterious devices, but because it understood how to manage uncertainty, propagate control across scale, and maintain consistency over time. Measurable outcomes reflect applied intelligence, embedded in processes, distributed across teams, and sustained through disciplined practice. This perspective dissolves the narrative tension between expectation and reality. The outcomes are no longer anomalies to be explained away or attributed to external intervention. They are the natural consequence of human optimization, methodical, deliberate, and highly effective. The contradiction is not in the civilization's capacity, it is in our tendency to underestimate it. By reframing the question in terms of capability, process, and optimization, we can appreciate the extraordinary sophistication of these constructions without invoking unverified or mystical explanations. Ultimately, the reframing offers a broader insight. Precision, accuracy, and measurable control are not exclusive products of modern instruments. They can emerge from a disciplined interplay of observation, iteration, and procedural knowledge. The pyramid base, polygonal wall, and modular city become evidence of a principle that transcends geography and culture. When human ingenuity is applied systematically, measurable outcomes can exceed expectations, even when tools appear rudimentary. The contradiction, once framed as lost technology, now becomes a lesson in the underestimated power of applied skill. And so the transformation occurs. The question is no longer, how could they do it, in terms of mysterious methods or instruments? The question becomes, how did they optimize capability? The realization is subtle yet profound. Ancient societies engineered solutions within the constraints of their environment and tools, achieving measurable precision through process, discipline, and systemic optimization. The apparent impossibility is dissolved, replaced by admiration for the application of human intelligence over time and space. This reframing reshapes the lens through which we study the past. It encourages a technical, grounded appreciation for procedure, iterative method, and tacit knowledge. It emphasizes that capability is not a function of technology alone, but of its application in context. And it prepares the viewer to see every ancient monument, every interlocking stone, and every aligned axis not as the product of mystery, but as the measurable evidence of systematic human ingenuity. And that realization changes how we read the past. The stones remain. Across deserts, mountains, and river valleys, they bear witness to a precision that continues to defy casual expectation. The base of the Great Pyramid deviates by no more than 12 arc-seconds. Inca walls fit with millimeter gaps. Angkor's causeways and temples maintain proportional consistency over kilometers. These are measurable facts, verified repeatedly by surveyors and engineers. They are not anecdotal, symbolic, or speculative. The evidence is tangible. And yet the contradiction persists. The tools documented, ropes, plumb bobs, water levels, sighting instruments, should not in theory have permitted such outcomes. Modern replication attempts, even with careful planning and iterative correction, struggle to match the measured precision without resorting to instruments far beyond those available to the original builders. The tension between expected capability and actual result remains unresolved, not because the results are impossible, but because the methods that produce them are only partially visible to us. Tacit knowledge, iterative verification, and disciplined process appear to have amplified rudimentary tools into instruments of extraordinary control. This forces a sobering recognition. The past was not primitive. It was precise, systematic, and optimized in ways that challenge the linear assumptions we impose on human progress. Civilization did not stumble toward complexity by trial alone. It engineered consistency, control, and reproducibility long before modern instrumentation. We measure outcomes and marvel at them not because they are mysterious, but because they reveal human ingenuity expressed through method, skill, and observation. The stones, in their measured exactness, demand a different kind of respect. They are not enigmatic relics or cryptic messages. They are proofs of capability. And sometimes, exactness, silent, immutable, and irrefutable, is far more unsettling than myth. Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.